this was to figure out if plasma was an efficient energy source. And I think they can hear me.
I can't
So,
hear you.
You gotta be like 25% louder.
Alright, the purpose of this was to figure out if plasma is an efficient energy source. We'll show that later. And then to see if the thickness of a piece of glass affects how long it takes it to break when there's plasma in it. So we hypothesized that plasma is not an efficient energy source of renewable energy. It's not. And that, and we're giving it what?
I said spoilers.
And that the thicker the glass is, the longer it would take to break, which makes sense. And then I'll explain the equipment later on. Alright, so our procedure, the first thing we did was we wanted to figure out how much energy was going into the microwave. So we used a WhatsApp Pro to figure out how much energy was going from the outlet into the microwave. And then what we did was we heated up water and used Q equals MCAT to figure out this energy going in. Then
we used the water because we approximated the size that the plasma would be when we created it in the microwave. So we wanted to see how much energy would be going into that volume or surface area. So that's why we used a small bowl of water and heated that up to see how much
energy. And that gives the energy in there. And then that was part one of our lab to figure out if it was efficient. And part two, we got glasses of different thickness to see if how long the explosion would take. And
So, the background, for those of you who don't know, plasma is a cloud of protons, neutrons, and electrons, where all the electrons have come loose from their respective molecules and atoms, giving the plasma the ability to act as a whole rather than a bunch of atoms. So, how can you make that in a microwave? What happens when you burn things is that new molecules are being formed, so electrons are flying off and creating different molecules. So, when you put a flame in a microwave induces a electric and magnetic field, and that just sort of sweeps the electrons away and takes them out of their respective molecules and creates the plasma blob that you'll be able to see in the video. Yeah, it's a really cool thing. It also sort of buzzes. We didn't look into that, but it buzzed at like 120 hertz, I believe. So that's like a future experiment thing that would be really cool to look into. But you'll hear the buzzing too, so watch out for that. So we did this because they are looking into fusion as a nuclear energy source. And basically they are trying to control plasma and make it efficient so that we can use that as an energy source, which is really cool. How would you control that? So there are things called plasma walls, which are just containers that are able to withstand the heat of plasma. Right now we are actually making, like, the fusion is happening at 10 million degrees, which is, I think, 5 times hotter than the sun, they said, because we have a different environment on Earth than the sun has in space. So it's super difficult to build walls that can withstand that heat. And also there's another thing that's a helical magnetic field that will also control the plasma, which I think is really cool. Yeah, and how to make plasma efficient. To make it efficient is to make the walls not leak the heat and to have the plasma walls hold all the plasma in without losing any, which is a very difficult thing, and spoiler, hasn't been done yet. So who's researching plasma? There are 3 professors. One of them's from MIT, and the other 2, I don't know. I think they're all working at MIT though, to work on the nuclear fusion and everything. And yeah, they're doing some good research, but they themselves don't see it as a viable source of renewable energy within like the next 20 years. They don't really see that happening yet because we don't have the technology.
Alright, so this is a video. You'll see the beautiful filming guy.
What does the C stand for?
Chops.
Maybe if you paid attention at the award ceremony last night, you'd know. Harry pronounced it wrong.
Oh, there's no sound, sorry.
Pay attention to like when the plasma goes in, it like makes little cracks, so that made it kind of like hard to see how long it took the glass to actually crack. Like you can see it forming.
And what exactly is in that container?
It's a glass and that's plasma.
It's just, you just light a match.
You light a match
stick
and then
it in
start
there.
a microwave, and then it creates plasma.
And then it goes. flat.
And then, yeah. So that was our second experiment. So our first one was finding out the energy going in. And then our second experiment was figuring out the blow up time and the thickness of the glass to see if there was any correlation.
Alright, so this is our data. So this is what we got when we heated up the water using Q equals MCAT. And then the energy of the microwave was just from the integral of what we got on the WhatsApp Pro. And if you divide those, you get this column. And then when we average it out, the average efficiency was like 11%, which is obviously not good. And then we didn't really get a good relationship on the time versus thickness because of, and we'll talk about the error a little bit later.
Yeah, but yeah, the efficiency is super low, but also because we don't have plasma, also is in a microwave that's not very well insulated, so that also makes sense.
Alright, so the graphs, this is the integral I was talking about on how we got energy from the WhatsApp Pro. And then we created a graph of thickness versus, or time versus thickness, but as you can see, there's no real relationship.
You've got a point here, 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 there.
Okay.
So we decided not even to put a linear fit on. Yeah, I don't know. So that's a sample graph of our taking the integral of power versus time to figure out the energy. And so our conclusion is that plasma is not yet a renewable or efficient source of energy, but it's possible that it could be in the future, which is super exciting. Possible relationship between thickness and time to explode if the glasses did not taper. What we found is mostly the glasses were thinner on the edges and then they got thicker at the bottom. And I think that if we would have had, and we also went to Savers to buy our glasses, so they were in like no way made of the same batch of glass, which could also affect the time to explode. So we think that if we like were in contact with the manufacturer, had them make specific different glasses of thickness, but the same thickness all around of the same batch of glass, then there would probably, hopefully, be a relationship between time to explode and thickness of the glass, but we don't have the ability to do that. So
and the reason the tapering glass makes it hard is because if part of it's thinner and then thicker, you don't know exactly where it's gonna explode to measure like which thickness is extremely relevant.
Yeah, and the plasma also moves around in the microwave as it turns, so it's like heating random spots, so that was also a difficult part to control. And lastly, we learned do not blow up ceramics. We had bought like 10 mugs, and unthinking, we just tried to blow them up, but if you think about ceramics, they have to be in a kiln, like fired in a kiln that's like 2,000 degrees. So they withstood all but one. Our first one blew up really quickly, and we
Which made it hard because we were very excited.
Yeah, we were excited. We were like, okay, we can do this. And then the rest didn't blow up. We assumed the first one blew up because there was like an air bubble in it, and that got too hot and it exploded. But yeah, don't blow up ceramics. Try this with glass.